Hi and welcome. And I'm so happy to see that you have taken the time to join the webinar today. And I look forward to get started right away. We will start off by looking at the context of where servo meters are being used and some of their main properties before we dig into the different technologies. I've also excluded spectrometers and other scintillator-based detectors in this webinar. But we'll cover ion chambers, Gauge-Müller tubes, semiconductor diodes. It's important to know that all of these have their pros and cons. And by the end of the webinar, I'd also like to introduce our recently launched Xray 452, which actually combines different technologies, and we look at how that provides the measurement behavior it has. During the entire webinar, as Göran said, you can ask questions via the Q&A tab, and we'll address as many as possible after that. Before we move on, I would like to do our first poll and ask you all, in what environment do you primarily use servo meters? So could you please take a moment and answer the question that will pop up momentarily. Servo meters are being used wherever there are or could be radiation present to control and minimize the unnecessary radiation to staff, patients, or to the public. It may be in hospitals for testing tube leakage or wall leakage, scattered radiation in the room, in nuclear medicine departments to check for contamination, or at radiotherapy departments. It can also be used in the industry segment to control objects or circuit boards in an assembly line for non-destructive testing, to scan containers at border controls or in the food processing industry. And of course, nuclear power plants and also first responder units are other groups that are in need of servo meters. So now that you've taken the first question, let's try the other one right away as well. Do you use several servo meters to cover your measurement needs? When we consider and look at properties of a servo meter, it's important to look at what's important to you. There are so many different applications and areas where they are being used. It must come back to what's the best for you and your specific task. There's a huge amount of different servo meters on the market. Here's a list of some key properties that are often looked at when considering servo meters. Whether they are important in your job is again very dependent on your specific task. If the meter has a high sensitivity, it will become easier to detect small variations of radiation. If you have a fast response time, it's easier to detect short pulses or when sweeping a surface. Whether you have a wide dynamic range or not tells us whether you have a risk to saturate the instrument or not. And you can also have a wide and flat energy response. And if you do that, you have a meter where you can more or less trust the readings you see on the display. Apart from the radiological aspects and functions of a meter, you may also need to consider things like, do I save time or can I get my work done more efficiently if the meter starts up in a couple of seconds instead of having to adjust in a few minutes? Will I benefit from having a meter that is easy to use and operate? Is sound important? Or could a sound be helpful, whether it's for listening for radiation or setting threshold alarm levels? I can save data for reports if I do that. Am I indoors or outdoors? And do I need a meter that can handle rain and dust? And is the size and weight of importance? Could I benefit from having a meter that can measure multiple quantities in one and the same? With all this in mind, let's take a look at the different technologies, starting off with ion chambers. An ion chamber is a gas-filled chamber, usually air, with a voltage applied across two electrodes, which create an electric field. Radiation then ionizes the gas and forms ion-electron pairs that move towards the charged plates and creates a current. Current is what's being measured and is proportional to the amount of ionizing radiation that hit the chamber. The ion chambers are built in many different shapes and enclosures and housings. One way to increase its sensitivity is to change the size of the chamber. If you have a larger volume, we get more air that can get ionized and therefore a higher current to measure. This makes the meter more bulky and potentially more fragile, unfortunately. You can also increase the risk to partly irradiate the chamber if you measure in a beam of radiation. That would cause us to underestimate the dose, because you need to expose the entire sensor to get the right values. That goes for all survey meters. Another way to change sensitivity is to squeeze in more air in the same volume. This can be done by pressurizing the chamber. Again, more gas equals more ion-electron pairs and a stronger current that we can measure. To keep the pressurization, we now need a thicker chamber wall. And if the pressurization is high enough, there's a chance the meter gets classified as hazardous material, which causes more administration and costs when transporting the meter. Another drawback, again depending on the application, is that the thicker walls also stop low energy photons from reaching the chamber. And this causes the meter to lose response in the lower energies. The vented chamber can detect beta radiation and have possibility to measure skin dose, of course depending on how the housing and design. Typically, they also have a more flat energy response. This shows the energy response graphs of a vented and pressurized ion chamber, where we can see that the pressurized one, the one marked green, drops in response at the lower energies. Gallium tubes, or GM tubes, are also gas-filled chambers and with a high voltage applied across two electrodes. The ionizing radiation that hits the GM tube generates an avalanche of ionizing events. This discharge event of the tube voltage corresponds to one count in the gallium tube. Right after this event happens, the GM tube is paralyzed and blind to radiation for a short period of time. The table you see shows the signal from an ion chamber and GM tube with different amount of radiation. You can see that you have high or low current with the ion chamber instead of high or low count rate of the GM tube, depending on the dose rate. This also means that the GM tube becomes less sensitive to noise because the pulses are the same height all the time. There is a wide range of GM tubes available in all sorts of shapes and sizes. What they have in common is, though, that they have a more limited dose rate range compared to the ion chamber and a non-flat energy response. The graph at the bottom right is the energy response of a GM pancake tube that has a thin mica window. So over to the semiconductor diodes. These are robust because they are made out of solid material, and it's normally silicon. No gas-filled chambers or so. When the radiation hits the diode, it generates free electrons and a current that can be measured for further processing. Diodes have a sensitivity of up to 1 million times higher than that of an ion chamber of corresponding volume. You can really build these really small. Semiconductor diodes do, however, have a high energy dependence that needs to be corrected. This is done by using several channels of diodes with different filtration in front of each of the channels. Signals can then be combined and processed to create a flat energy response. Another benefit with the different channels is that you can get more information from the radiation environment. And with this information, it's possible to measure not only the dose and dose rate, as with the other meters, but you can also measure mean energy. And for example, when these instruments are used for performing in-beam measurements in diagnostic X-ray, it's very convenient to get the total filtration as well as HVL, which is the half value layer, automatically. So let's see what we have looked at right now when it comes to the ion chamber, GM tube, and semiconductor diodes. We move on. It's time for one last poll. I'll give you some time to answer the question, what type of technology does your current servometer have? So, Göran, how did we do with the first two polls? Have we got the results?
Yes, we do. The first poll question was, in what environment do you primarily use survey meters? And 45% of you listening is in the hospitals, 11% in industry, 3% in nuclear power, and other segments was marked by 8% of you, and 32% did not answer. And we also have the results from the second question, which was, do you use several survey meters to cover your measurement needs? And the result was that 59% said yes, 14% said no, and then we had no answer from 27%. Thanks a lot, guys.
Yep. All right, so let's get back to the summary and looking at the ion chambers. They typically have a wide dynamic range. You should consider the size versus the sensitivity, or having a pressurized ion chamber versus sensitivity, and with the lack of a little bit less energy response in the lower ranges. GM tubes typically have a high sensitivity, but a non-flat energy response, which needs correction to read correct values. They may be great for finding radiation. They have a limited dynamic range, but a fast response time, and we need to make dead time correction for the time right after a discharge when the tube is blind to radiation. Semiconductor diodes are small and robust. They have a fast response time and a wide dynamic range, but a temperature dependence that needs to be adjusted for in the instrument, if the range of the instrument requires it. As just mentioned, they also need several channels to adjust for the non-flat energy response. So, Göran, have we already got the reply from the last poll?
One second, and we'll check here.
I can say in the meantime, as you can see here, it is really different. The different technologies have their different pros and cons. It's really up to what they are being used for and what is your need in that sense.
Okay, sorry about the wait. And so the last question, poll question, was, what type of technology does your current survey meter have? And the response is that ion chamber is used by 50%, GM tubes by 33%, semiconductor diodes by 22%, other by 8%, and don't know 4%, and 35% did not answer.
Right, interesting. So when we look at this, what would the properties be of an ideal survey meter? Again, depending of course on the application it's being used in, but it would be really nice if we could have a small instrument with a wide dynamic range that have a high sensitivity with a flat energy response and a fast response time. That would create a great and very versatile meter. These are the properties that we have thought about when we worked and developed the new Xray 452 meter. And I'll now give you a brief introduction to how this has been achieved with that meter, with the technologies we have chosen. The 452 is actually based on semiconductor diodes in combination with a Gauge-Müller pancake detector. We have the GM pancake in the middle, where it can be used as an unfiltered, high-sensitive sensor when looking for contamination and radiation. Here we get counts per second and counts per minute. Surrounding the GM tube are an array of semiconductor diodes with different filtration to create 4 channels that are used to accomplish that wide and flat energy response. With the diodes, we can also read out the mean energy of the radiation. The way it works is that when the dose rate increases, the silicon diodes automatically take over and continue to capture dose long before the GM tube would potentially get saturated because of its limited dose rate range. This, as a whole, results in an instrument with a high sensitivity combined with a wide dynamic range. In front of the GM tube, we use 2 filtration lids to get a flat energy response also for the GM tube and at the lower dose rates. One filter is for air karma, measuring in gray, rad, or Röntgen, while the other one is for ambient dose equivalent, measuring in sievert or REM. So this is one way to combine different technologies to achieve best possible meter from that standpoint, to get that high sensitivity, fast response time, a wide dynamic range, and a wide and flat energy response. It gives us that versatile servo meter that can be used for many different applications and measurement scenarios. The 452 in the meter, we also have a fast startup time where it takes a couple of seconds before it's ready to measure instead of a couple of minutes, which is sometimes needed. We have an intuitive and easy user interface, at least what we believe. You can turn on or off sound or set alarm levels. It automatically saves data, which can be exported for reports or later processing. And with its high IP classification, it can also be used both indoors and outdoors in rainy and dusty environments. And it's lightweight and has the possibility to measure multiple quantities with help from the 2 different filtration lids. So again, it all comes back to what's important for you and your daily work. How can your instrument make your day easier, more efficient, and what are the key features you need? Do you need 1 meter for one task, or do you need one that can do multiple? Would you benefit from that, for instance? This is the Xray and Fluke biomedical servo meter range that we offer. And as you can see, they are actually all based on different technologies. 452 on the combination of semiconductors and a GM tube. We have an X2 survey sensor, which is only semiconductor diodes. The 451 models are both ion chamber based, one that is pressurized and one that is vented. And the ASM 990, which is GM tube based. The 452 is that versatile multi-purpose high sensitivity meter that can be used for many applications, from finding spilled contamination and measuring scattered radiation from Xray machines and linear accelerators, but also for outdoor use in high or low radiation environments. X2 survey is specifically made for the diagnostic X-ray room, where it fits great with its small size and data capacity, where it can save waveforms. 451P and 451B are both multipurpose meters. The P, which is the pressurized version, is a bit more sensitive, while the B is vented and can also detect beta radiation. And finally, the ASM 990 or 993 is an unfiltered GM tube, which is great for finding spilled sources and contamination. With all this said, I just want to get back to the technologies we have addressed today. And as you have already noticed, there is no technology that is better than the other, generally speaking, as they all have their pros and cons. It really depends on how the technology is being leveraged by the developers of the instruments, and then, of course, in what environment and for what application the instrument is being used. Said, I would like to open up for the Q&A. And Göran, have we received anything on the question? Feel free to continue to ask as well, of course.
Yes, we do have some questions, and I will take them in the order they came in. And the first one is whether we can use the 451P to measure X-ray leakage.
Generally, yes. X-ray leakage from a diagnostic X-ray machine, for instance, with no problem.
All right, very good. So the next question is whether do you recommend that someone have both lids, or should the lid be selected based on the country in which it is being used?
This is a good question. Normally, if you look at it on a global aspect, in the US, it's more common to measure in Röntgen, while in Europe and in Asia, it's more common to measure in Sievert or Gray for that matter. So, but you still may want to measure in REM in the US. So both lids are not bad to have, but it depends on your application and what you need.
You can purchase the meter in different configurations, different lids.
Yeah, that's right. So you can purchase the meter in either with one lid or the combination of two lids.
All right, good. So next question. Can the 452 measure high dose rate? If yes, what are the range? What is the range?
So the 452 measures up to 1 sievert per hour. That would correspond to about 114 Röntgen per hour. If you convert it with the air karma lid.
So pretty high.
So pretty high, yes.
All right. Many questions here. We just take the next one. Can the 452 measure pulsed radiation?
Yes, it measures pulse radiation quite well, and it covers everything from the single pulsed X-ray machines in the hospitals to linear accelerators that have a very high frequency pulse radiation.
Great. Next one. What is the recommended frequency of calibration?
We normally recommend an annual calibration of our meters, independent of what type of instrument it is actually, just to make sure that you have the most up-to-date software, as well as making sure that your instrument is performing as it should.
Next question, it just says dead time is built in the survey meter. I don't know if you can interpret that a little bit?
I could guess that, yes, we perform dead time correction with the survey meter 1,000 times per second, actually. So we do that a lot to make sure that we get as much and as good dose rates as possible.
We also got a comment here that it may be helpful to state that if you do not purchase the full kit with both lids, you cannot utilize it without the lids for counts.
Yes, when we get into the details of the actual product of 452, I can get into that. We do have 3 different models. One that only measures with the air karma lid, one that only measures with the ambient dose equivalent lid, and one that can measure with both lids and also with the GM tube open.
Okay.
I have not got into the details of the product in that sense.
Okay, well, good to have that sorted out. So next question. How does the cost of calibration of the 452 and the X2 compare to the cost of calibration of the 451? If we start with the 452 versus the 451.
They are fairly similar in that sense, but if we get into the details, I would really like to refer to the sales representatives of each regions. But it's in the same line as the 451.
Okay. And with the X2, it will of course be a lot about what configuration the X2 has.
Yes,
I guess
there are so many different models of the X2.
How accurate is the 452 in measuring pulse radiography in industrial radiography, such as nanosec pulses?
Yeah, so we have the specification of the 452 actually says that we specify it down to single pulses of 5 milliseconds, and then you have pulsed counting. It increases so that you can measure nanoseconds of up to 100 hertz or above. We do have a small area where we have not characterized the 452 at this point, but we would assume that we underestimate the dose a little bit, which is quite common on single exposure nanosecond pulses, like, for instance, handheld industrial X-ray machines. So we'll need to get back to that in detail.
Thank you. Next one, what is the directional response of the 452? From the sensor's placement, it looks like it would have issue in complex scatter environments, angular dependence.
We have provided the angular response graphs in the user manual, which you can find on the website. We do have a great response when it comes to plus minus 45 degrees in all energies. And then it depends on if you have higher or lower energies you're measuring, where you can have loose response if you measure from behind, of course.
But the question here, if you have scatter from like several directions, has that been a problem in our testing or anything like that?
No, we have an cumulative algorithm, so it captures everything that it can see. But again, if you do measure from behind, it will have a different response than if you measure from the front of the instrument.
Yeah, but maybe scatter radiation is not typically qualitative, or typically qualitative more than quantitative.
Yeah, depending on where it comes from.
Okay. Okay. Thank you. Yeah, so that was also, there's another question, how does it deal with instant angle issues? I guess that is very similar.
Yeah.
So we move on to the next one. How easy is the 452 to decontaminate?
It is fairly easy, though, since it has an IP classification where it can withstand some rinsing water, and so you can clean it off quite easily.
The questions keep coming here. Very great to see that. Next one, can the 452 be calibrated by the end user, or must it be sent to a depot for calibration?
At the launch and at this very moment, we are the one, RaySafe and Fluke Biomedical are the ones that can calibrate and adjust the 452, and we'll investigate further when or how we will approach that you can do it in the field.
Okay. You mentioned in-beam measurements. Can the 452 be used for taking in-beam measurements for HVL?
No, maybe that was a misunderstanding. When I talked about in-beam measurements, it was more make sure that if you have a radiation that is not in the whole environment, you need to make sure that you expose the whole surface, but you should not use the 452 for in-beam measurements. There we have our diagnostic X-ray range,
okay,
which we have not even talked about at this webinar.
So the next question, I think I can answer. It says, unfortunately, I missed the beginning of the presentation, and will it be emailed out? So we'll just repeat that the recording of this webinar will be found on our website shortly. So stay tuned for that. Next question, in the presence of neutron, will the silicon detectors have signal inducement?
We have tested the 452 and it is not sensitive to neutrons. So not a neutron detector, and it's also not affected by them.
Okay. Next question, is there a specific type of calibration request needed when using this meter to capture scatter from industrial cabinet type of X-ray scanners? So I think the question is whether it needs some type of other calibration or setting or anything like that to cover that particular measurement.
We don't have any application notes written for the 452 at this point, and we need to take each measurement case by case, and if that would be needed, we can help out and develop that. But at this point, we don't have.
So you would need to know more about the specific X-ray as such.
Yeah.
Even though we know it's quite versatile for any type of radiation.
Yeah, we would need to know and perform measurements with references as well to make sure that what should the meter show.
We do have the energy response graphs and all that in the documentation.
Yeah.
So what is the energy which 452 is measuring and displaying? For example, 51 kiloelectron volts was displayed in the example. And how is it defined from a broad spectrum?
The parameter we're referring to is the mean energy parameter of the 452, and it's we calculate that through the different channels of the diodes, and because we need the diodes, we can only calculate mean photon energy if the diodes are active. So we need some dose rate to get that that parameter to show. But it shows the mean photon energy between 20 keV and 600 keV. If that helped.
We hope so. So next question is, how is it when measuring analytical type devices like XFR or XRD? Do you know those devices?
Well, no, I don't follow exactly.
Okay, we'll see if whomever sent that question can define it a bit more, and we'll move on to the next one. Do the Xray 452 can it be used to measure average energy of scattered radiation from a solid water phantom inside a radiation therapy vault? Can it also measure the dose rate and dose?
It would be very interesting to test. But if the mean energy would be in the range of 20 to 600 keV, and we are within the right dose rate range, we may be able to capture it. And when you look at the high energy rooms of therapy vaults, even if you have the machine set on many mega electron volts, the mean energy is often much lower, so a couple of hundred, or maybe up to a mega electron volt, but often lower than that.
Okay, great. Next question, can it be used in mega voltage environments?
Yes, we have the energy response graph that shows how it performs in that environment. But as I said, if you do measure on linear accelerators or such, mean energy in those environments are often much lower than what's set on the machine.
Next one, for Xray cabinet shielding surveys would the 452 fill the requirement, or should we continue to use a 450 or 440 RF?
So I believe the 440 RF is very well shielded for electrical fields, and it would be very interesting to try out, even if the 452 is not made for that extreme environment, but it is quite well shielded already and would be really interesting to test out.
Now we got some more information here on the XFR and XRD. As XRD is X-ray diffractions, and XRF for X-ray fluorescence.
Well, I would assume we do measure all right on those devices.
Okay. A final question is also what the price is of this meter.
Interesting question. So the new meter, the 452, is priced in the ballpark of where we have the 451 models. So it's not 3 times higher or something like that. But please contact your local sales representative to get the exact prices, and if you want a demo or such, and we'll be able to help out as much as possible.
All right, we were just getting, maybe a question from another source here that we were trying to track, but unfortunately we don't seem to get hold of it. But anyways, and thank you everyone for joining our event today. After the webinar, you will be given a short survey. Please fill that out and let us know how we did and how we can better serve you in the future. And of course, visit us at flukebiomedical.com or raysafe.com to learn more about the 452 and our other survey meters, and get additional information, some of it that we refer to here, see demo videos and more. And again, thanks a lot for your time and attention, and enjoy the rest of your day. Bye everyone.
Thank you. Bye bye.